we can only reduce the flow. So okay, normally what you start with is no flow. Right, I have to start this. But that would take a long and boring time. So I just picked a path to start with, okay? And so I started with that original flow of 12, 12. Yeah, I just had 12, 12, 12, 4, 4, 4. I mean, if you start with all zero flows and you build the residual, and then, ooh, there's going to be a path, because if there isn't a path initially, then you can't send anything. And then you do this, and then at some point you're going to get this. So I started 2 steps in. So here we're going to say, you know how to find paths. That's not what this lesson is about. You can go here, you can go, oops, you don't want to go there, forget I said that, because then you're trapped. You can go there, you can go there, you can go there, you can go here. Actually, that makes sense because last time the minimum was here. So there was still sort of, and there was no other occurrence of the minimum, so there was sort of still slack on the rest of this. And there was slack here. So, oh yeah, actually this wasn't the best path that increased it the most, because we could have actually gone here with 7. We could have gone here with 7. But we'll, okay, so let's do that. So here so this was just a path. This is just a path. And so we say, okay, we go here to here. We go from Vancouver to Calgary. We go Calgary to Regina. Regina to Saskatoon, and Saskatoon to Winnipeg. What's the minimum capacity along this? So it's 9 here, 6 here, 3 here, and 4 here. So the minimum is 3. So now we try to find of the 3 blue markers, because I keep using black, and I should just buy black markers, but now I have loads of blue markers. So and one of them works, I think. So now we're going to add 3 to everything here. So this is now going to be, no, it's not this one. And now I have the black markers. So this is going to be 7. No, it's not that one either. This is not going to give me a reputation for efficiency. Okay, yeah, it's that one. So we add 3 to that. This is now 11. Now this is now 7. And this is now 19. Okay? So now we're sending 23 crates of pucks every day from Vancouver to Winnipeg. And we know, just like it's obvious right from the word go, that we could never send more than 24 because there's this obvious cut with total capacity 24. So 23 out of 24 is really good. Now, which of these is the decent black marker? Where did the other blue markers go? Oh, they're up there. And one of the black markers. So I've got the good stuff down here. So one more residual. So this is still 16, 12. We can reduce this by now 7. We can increase it by 6. We've got 8. net change that to by 8. We can increase this by 6. This is still 9. We're not using that. Okay, never mind. This is now, we can increase it by 3. We can decrease it by 11. So this is now, we can only decrease this by 7. We can't add any more to this because it's at capacity. So now we can increase this by 1, and we can decrease it by 19, and we can only decrease this by 4. Okay. So, is there a path? Well, if there is a path, let's look for the path. It would have to go here, right? Because this edge is not there. So we're looking at the path, we go here. If we go here, we're stuck, right? Because we can't get out. I mean, we can go and then come back. We can't go across that edge. We can go here. So we could, I mean, let's just draw the paths we could take. We could go here, we can't go anywhere else. We can go here, now we can't go anywhere else. All right, so this is 4. So, now we cannot find an augmenting path because there is no path from S to T in the residual. So we can't add anymore. So, let's see, does that give us a cut? Well, we're going to take the cut, which is here. I'm just going to make sure that this works. Yes. Okay. Yes. This is going to give us a cut, right? So these vertices are the things we can reach, and these are the ones we can't reach. Okay, so this cuts the graph into 2 subsets of vertices, reachable from those on the S side and those on the T side. Now, if we look at our graph, our extremely messy graph, and we look, now it's an extremely messy graph, and we look at those, so this is the cut, okay? And then we look at the total capacity on the edges going from the S side to the T side. Right, because there's this max flow min cut there. Now, I didn't actually say it, but the idea, if you look at it, you take a cut and you look at the amount of stuff going from the S side to the T side. Sorry, I was just saying the total capacities. But you don't care about the capacities going from the T side to the S side because you're not trying to send stuff that way. You're trying to send stuff from S to T. So if you look here, I will actually draw this down here in green because I never use the green marker, and so it's nice and good. Right, so we have this graph, da 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 da. Okay, now this is what we want. Now, this edge, and this edge are going from the S side, so this is the S and this is the T. And these edges cross the cut going from the S side to the T side. What is their total capacity? 12 plus 7 plus 4. It's 23. We've found a cut, an ST cut. Oh yeah, so the other thing is it has to be an ST cut because it's like, oh, I could cut some other vertex out of the graph. No, it's an ST cut. We care about like separating the S side and the T side. So these have total capacity, so it's 12, 7, and 4. And since by deleting these, we can separate, now there's still this edge going across, but it's going the wrong way. We can't use that to send anything from S to T. Right, so if you can find this cut that where all of the edges going from the S side to the T side, you take their total is 23. If you can get a flow with that much, then you know by the max flow mean cut theorem that you're done. And the max flow mean cut theorem says that this is tight. That if you found a max flow, there will be a cut that matches that. Okay. Oh, but it's not that bad. We still have plenty of time. Any questions? Oh, right. So we want to do maximum bipartite matching. So what you would do to find a maximum flow is, so this is just going over this again. You have your graph, your extremely messy graph now, and you pick a flow, and then you build the residual graph, and you try to find a path from S to T. This is an augmenting path in the original. You add that much flow according to this path. You add that to this graph, and then you build the residual again, you find a path, you add it to the graph, you build it, and when you finally build the residual and you can't find a path, that means that you can find a cut, and you're done. Now, what's the running time? I forget. So the running time is tricky. Because if all the things, so in this case, you're guaranteed to terminate fairly quickly, but there are these pathological cases. So if it's integers, actually no, okay, if it's integers, definitely. So you have these, so this is called the Ford-Fulkerson method. There are other methods which don't do this, so let me see, does this have, what is the, I should have done this before. Oh, I'm gonna have to do it from memory. So it's something like you have, this is the bad marker. How did this work? So I can put this in the lecture note when I eventually actually write some more lecture notes. So this is S, and this is T, and this is 1, and this is 1, and I think this is 1,000. This is 1,000. Something like that. Anyway, the problem is where you can force it to do this. you can force it to just add 1 at each step. So I'll find the example where it's like, okay, Ford Fulkerson gets stuck in these, yes, it's finding augmenting paths and it's incrementing the thing, but it's incrementing a really tiny amount. And so if you're allowed to have fractional capacities, then this can get really, really slow. There are faster ways, but we're not going to cover them because we're almost at the end of the course, and usually people don't do network flows in this class anyway. So it's I think it's something like if you start out with a flow that goes sort of 1 out of 1,000, 1 out of 1, 1 out of 1,000, then it's something, it's 1,000 out of 1,000, 1 and 1,000 out of 1,000. Yeah. Oh, right. So I think this is where then if you look at the residuals, you can't put anything across here. Here you can't put anything across here. So the best you can do is is put 1, 1, and 1. And then, so yeah, I think it looks basically like this diamond, and you can get into this case where it's like it's flipping it, it's increasing it 1 at each step. How come with fractional capacity? Because basically, if you have small integers, then, so if they're all integers, okay, but if the capacities are all integers, and you start with 0 flow, right? Then when you find a path here, the minimum is going to, the residual capacities are all still going to be integers. So if you find a path, it's going to have a minimum that's at least 1, right? It can't be like 2/3 or something like that, or 1/1000th. So if you've got small integers and your augmenting path, each time you augment, it's going to be like 1, at least 1. Then pretty quickly you're going to find the maximum flow, right? If the maximum flow is 23, on this it has integer values, so it's at least 20, it's going to take time, at most like 23. Whereas on this example, which I will actually look up, and I didn't, until just recently, until just this minute, I realized that I didn't realize I was going to show you this, and I thought I had it memorized. So, because I think, like, let's see what happens with it. This is almost right. So you would then get a residual that's 1,000, and you can't put, but you can put 2 this way. And you can put 1,000 this way, and you can put 1,000 here, so this is the residuals, and you can put 1,000 here, right? So if you look at this, it's going to, there is a path, right? So if you start this, and you start with a flow that's 1,000, 1, 1,000. No, this, because here it's 1. So if it's going to be 1, 1. Okay, I'll have to look this up. I will put it in the course notes if I actually get it written. It's 1, 1. Okay, so what happens if it's, so here it can't be 1,000. Anyway, there's this way. I think maybe if you find the maximum paths, it's not so bad. So if this were 1, 1, 1, this would be this would be 1, okay, let's do it this way. It would be 1 going back, 999 going this way, 1,000 going this way, 1 going back, 999 going this way, 2 going up, and 1,000 going this way. So if you're unlucky, I mean, you could go 1,000, 999 and increase it a lot. But if you choose the wrong path, you can go here, here, and then it's 2. So the 2, what you're doing is flipping this to 0 and increasing this to 1. So if you choose the wrong path, so if you just say, I'm going to find an ST path in the residual graph, and you don't say you don't look for the one that has the maximum minimum capacity or something like that, then you can get stuck in this cycle of where you're increasing it by 1 at each time, and so this, even though it's a tiny graph, it'll take you like 1,000 steps to get up to the actual maximum flow. Okay, so, right, so, okay, so maybe that's, I'm behind on the lecture notes, I'm behind on a load of stuff. I'm super behind on a conference paper reviewing. Behind on cleaning my apartment. I did get my taxes sorted out, so I'm not behind on anything that can get me sent to jail. This is good. I paid my taxes, but I only realized last week that on my account it said, oh, it hadn't arrived. So I called them, and apparently it did arrive. The system is running slowly, but yeah, otherwise that would be bad. So I caught up on something last week. Right, so let's look at this problem of bipartite matching. So people may remember matchings from approximations of vertex covers. So you have this bipartite graph where so yeah, let's put this person here. Right, so this is a directed bipartite graph. So you have one bipartition, another bipartition, and let's say you have, yeah, I think we're going to make it unweighted, just to make my life easier. So, okay, so matchings actually come up quite a lot. Now, they're usually, you get like more complicated versions where you have like preference orders and stuff. So there are things, so university students in Greece, they choose preference order. So if you get into matchings, you have these preference orders, and people really look for, people are interested in what you call stable matchings. So, so if you have a preference order, so for example, universities in Greece. So in the States, this is sometimes called the residence hospitals problem. And in Greece, this is how students get assigned to universities. So the students write some exam, and they list their universities in order of preference, and then the universities have a preference order of 22 seconds. Okay, I'm going to have to start again. So then what you do is you're trying to find what's called a stable matching, and a matching is stable if so some student may not get matched with their preferred university, okay, and some university may not, some university may not get their preferred student.